Hello, are you a student who has heard about quantum computing and have wanted to see how it works for yourself? Then you've come to the right place. Now, the words quantum circuit simulation might sound intimidating, but at its core, it's just a bunch of applied linear algebra. That said, a more familiar comparison to explain it would be with logic circuits that you covered in Comp Sci 121. In the circuits that you worked with then, you were using classical bits, which could have one of two definite states, 0 or 1. In quantum computers, we instead work with quantum bits or qubits, which can take on states that are arbitrary linear combinations of 0 and 1. Additionally, in 121 you worked with logic gates such as AND and NOT that would take in 1 or 2 bits and perform some Boolean operation on them. With quantum circuits, the gates are represented as matrices which modify the quantum bits that they act on. Although some quantum gates have parallels with classical gates, such as a poly X gate which acts like the NOT gate, some gates have functionality that's completely new, like the Hadamard gate which puts a pure qubit into a superposition, or the CNOT gate which entangles qubits. There's a link in the description with a more elaborate description of the math behind qubits and gates, but let's move on to the demo. Let's start with looking at the single qubit case. We start with the qubit in the pure 0 state. I can add or remove quantum gates to my circuit as I wish, and as you can see there's quite a variety of gates here, even if we don't have time to look at them all at the moment. If we apply the poly X gate, we can see that indeed it flips the 0 to the 1, and applying it again it flips it back to a 0, like the NOT gate. Applying the Hadamard gate, we see that our qubit is now in a superposition of 0 and 1. Now, another thing that distinguishes quantum bits from classical bits is inherent randomness. So if I were to measure this qubit, I can either measure 0 or 1 with equal probability. So let's try this out. First, I'm going to save my current qubit state so we can come back to it, because the measurement is going to collapse it. Now, if we measure and reload multiple times, we can see that we indeed have a 50-50 chance of measuring either outcome, and it's totally random. Alright, now let's move on to the 2-qubit circuit. This allows for some more slightly complicated operations. I'm of course free to apply any single qubit gate to these qubits individually, but there's also some cool things that we can do with entanglement by applying the 2-qubit CNOT gate. Let me load in a circuit I made that does just that. What entanglement means is that the measurement outcomes of the 2 qubits are highly correlated. Looking at the state we get from applying the CNOT, we can see that there's a 50-50 probability of measuring either 0-0 or 1-1. This means that if I measure one of the qubits to be in 0-1, then the other must measure to be in the same value. Another way of describing this is that I can't describe the 2 qubits individually, but can only meaningfully talk about the combined state. This is where much of the exciting quantumness of quantum computers comes from. Although this is a short video, I hope you found it interesting. Have a most wonderful day.